Good morning, everybody. Thanks for making the invitation, Boaz, Osnet, Gotti, with the help with the arrangements, and thank all of you for your time. So let me get right to the point. Greatness is possible. I mean, absolute, unbelievable greatness. And it's not just greatness here, and everything else is not great. Across the board, high-tech and heavy manufacturing, product design and production, manufacturing and services. Greatness is possible across all those different sectors. And greatness is not everyone does this and you're 3% better, 4% better, 5% better. Greatness in terms of twice as fast, twice as good, 10 times higher quality, 100 times better safety. That's the measure of greatness we're talking about when we say it's possible. That's my point today. The final point is that greatness is possible not because some people are born great and it's just a matter of coasting through life. Gotti mentioned Isaac Newton. One of his rules was that momentum gets conserved. All right, well, he also said this, so it's not as if you pop out of the womb and just keep going on a ballistic trajectory. Greatness is possible if you learn, practice, acquire, master, and finally apply skills that allow greatness to occur. That's the point of my talk. The rest is all detail. So if the coffee hasn't kicked in, take a nap, a little schluff, it's fine. But just remember, when you wake up, greatness is possible. It's across the board. It's possible by enormous dimension, and it depends on having certain skills. So in terms of building out the detail on this greatness is possible story, I'd like to do a couple of things. One, address the challenge to greatness. The challenge to greatness is complexity. And it's the complexity which requires the skills to discover our way to greatness. And after we establish what the challenge is around complexity, and we'll get into what these skills are. So that's the basic outline for the presentation. First, let me talk about the challenge that's the challenge for everyone to greatness. To give you a succinct picture, this is the challenge, the Ford Mustang. Now, when you look at these two cars, at first glance, surface appearance, they look very similar. And in fact, it's a tremendous credit to the designers of the first Ford Mustang that over some 50, 60 years, the integrity of the design is still attractive so much later. Now, there's a cliche, at least in English, don't judge a book by its cover. I don't know the Hebrew translation to that. There must be one. But don't judge a book by its cover. Don't judge a car by its exterior. As similar as these cars appear to be by styling, they're fundamentally different. Fundamentally different. Bear absolutely no resemblance to each other on the inside, what they can do. And the car on the far right, on my left, your right, is a much better car. And let me explain what I mean by better. This car was designed with two objectives. It should look good, and if you're designing a car in 1964, to look good means you look like an airplane or a rocket ship. And in this case, the airplane is the P-38 Mustang. So you look good and you go fast, and this car went reasonably fast. Now the car on the right still has the look good aspect to it. It actually goes much faster. This car is about 100 horsepower. The new one is about 300 horsepower. But not only does it go faster, it goes further because it has about twice the fuel economy. When it goes further and faster, it goes cleaner because it has nearly zero emissions except for carbon dioxide and water vapor. It goes further and faster, but also goes further and faster without breaking down. See, this car, you couldn't go very far, you couldn't go very fast, and you couldn't do it very much without fixing your car because it kept braking, which was true of any car in 1964. But this car goes further and faster without interruption. Not only does it do all that, but if you think about the problem of going further, faster without interruption, the chances are very good you're going to go to places you don't know. But you don't get lost in 2010 because this car has GPS. You don't get bored because it has satellite radio and MP3 players. You don't get uncomfortable because it has climate control. And with all of that going on inside the car, see, in 1964, the only thing you had to worry about is drive. But in 2010, what you have to worry about is drive. Where am I driving? How fast am I driving? Who are all the other people on the road with whom I'm driving? You also have to worry about where's the radio set, because I have several hundred radio stations. But this car has traction control, anti-lock braking systems, power steering, airbags, crumple zone. So even if you get distracted, you're still safe. It's a much better car. Not only is it a better car, it's actually a less expensive car. So if you were to pay inflation-adjusted dollars, you get a much better car for less money. And here's the other thing. With all the advances around the car, there have been tremendous advances around the making of the car. So not only can you get a better car, which costs less money, there are many more of them available. And again, let's think about this. Quality and functionality have gone up. Affordability has gotten much better, as has availability. And again, it's not 3%, 5%, but it's 10x, 100x improvements. So far, all good news. This is the challenge. The picture you're looking at here is the inside of the 1964 Ford Mustang. Engine block. On top of the engine block is the carburetor and air filter. In front of the engine block is the radiator to cool down the engine. You can't see it, but behind the engine block is the transmission to take power from the engine block out through the drive shaft to the rear wheels. Very, very simple. And as Gotti mentioned, this is an entirely Newtonian system, all mechanical. Very simple. It didn't actually do much other than look good and go fast, but it was very simple. This is the inside of the 2010 Ford Mustang. Now, if there are people in the room who are not car people, I challenge you to find the engine. It's in there. I guarantee there's an engine in there, and the way we know that is when you start this car, you don't turn the key anymore. You press a button. But when you press the button to start this car, it starts up and it goes further faster without interruption. And it begs the question, why is all this other stuff inside the engine compartment? Because Ford in 1964 was perfectly happy with an engine, carburetor, radiator, and transmission, and now you've got all this other stuff. Well, of course, the reason for all this other stuff is to give you all that further, faster, higher functionality, the GPS, the traction control, power steering, cruise control, active control, headlights, and so on and so forth. You had to put devices into the car in order for the car to do all these things better at less cost for more people than it did 40, 50 years ago. So we still have a good news story, though, right? Higher quality, better affordability, more availability, and better affordability. The problem we have is that if you're responsible for designing a Ford Mustang today, you have a much harder job than someone did in 1964. See, in 1964, you had about as easy a job as existed. You knew your device was made all of iron and steel. You knew it was all mechanical. And so what you had to do if you were to manage the design is ask, what are the objectives? And you'd find out, look good, go fast. And once you knew the objectives, all you had to do was hire mechanical engineers who, working off of some basic first principles, engineering tables, engineering charts, that sort of thing, could go into a room, probably not much bigger than this, with not many more people than we have in this room, and think their way through to an adequate design. Because if you just conserve mass, conserve energy, conserve momentum, and then do that with a little bit of calculus, you get this car. You can't do that in 2010. Because to get the car in 2010, if you have mechanical engineers into a room, they might be able to design the engine block. Not necessarily, actually, because the ones who designed it in 1964 understood iron and steel, but now you need people who understand aluminum. So you have to bring them into the room. So now you've got the steel people and the aluminum people, but still mechanical. But you can't design an engine just mechanical because it's got electronic controls for the valves. So you have to get the electrical engineers in the room. Then when you have the electrical engineers in the room, well, they can design all the circuitry, but unless there's software on top of that, it doesn't work. So you need the computer engineers in the room. When you've got the computer engineers in the room, you still don't have a working car because this car, in order to work, needs a fuel injector. Now, the fuel injector has its own mechanics, it has its own electronics, its own software, but it also has ceramics. So you need the material scientists in the room. But then you need other material scientists who understand rubber and plastic and polymers. And they're in the room. And then you have the people who come in the room who understand signal processing. The reason you need the signal processors is because you've got experts in sensor technology and telemetry. So you've started crowding the room with all these different experts, none of whom you needed in 1964, and in fact, many of whom didn't exist in 1964 because we didn't know the science and didn't know the technology even existed. It's not like we didn't understand it. We didn't even know it existed in 1964. So you've got all these people crowded into the room. And at this point, imagine this room, we need a much bigger room. Right? But it's not just the number of people in the room and the different specialties and disciplines they have. See, the thing is, 1964, it wasn't only just a few specialties in the room. The relationships themselves were very, 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 very simple. So you say to your mechanical engineers, make me a car that goes fast. They say, go fast. Okay, well, that's a ratio, something about mass and horsepower. Again, Isaac Newton at work. Horsepower comes from the engine size and displacement. So they decide the size of the cylinders and the number of cylinders. Then they say, well, now that I know the displacement of the engine, I know the horsepower coming off it, the heat being generated, set of calculations onto the radiator. That gives them a set of calculations onto the transmission, set of calculations onto the drive shaft. One decision cascades to the next one to the next one, the next one to the next one, the next one to the next one. So you can put people in a room, and it's like dominoes. Topple one over, and then the others have to topple in a certain way. 2010 Ford Mustang is a very, very different product. Not only do you have more specialties in the room, but the relationships have changed fundamentally. Absolutely fundamentally changed. See, the thing is, simple decisions. For example, how much glass on the windshield? 1964 is a domino-like decision. Add glass, change the location of the post, change the location of the post, change the weld points, change the weld points, change the manufacturing process. Decision cascades to decision, cascades to decision, like a waterfall. You make a decision about the glass on the windshield in 2010, you made a decision about the cooling. Because people in 2010 drive with the top up. Why? Because they're going further, they're going faster, it's louder, and they have a great stereo on board to which they want to listen. So add glass, you have to cool the car more. You have to cool the car more, you need a bigger compressor. 2010, you don't have room for the compressor. So now you have to start negotiating with all the other parts of the car and the specialists who own those other parts on where you're going to put the compressor. Not only do you have to negotiate on the physical compressor, the physical size of the compressor, you have to negotiate on the power flow. Because it's not so simple to draw power off the engine, run into the compressor, when that power is also being asked to go to the traction control, the cruise control, the GPS, the entertainment, and everything else. That problem of many, many more specialties, many more functions, many more disciplines, being connected, not in a waterfall cascade, but now like a spider web where the decision here connects to this decision, this one comes down to this one over here, this one over here, this one over here, on and on and on, is the reality of modern life. The problem Ford encounters today is that in order to get an adequate car out the door, they have to manage the incredible complexity of the product and the incredible complexity of the process to make that product. And I'll give another example, because as I said, this greatness thing is possible not only in manufacturing, but in services, not only in design, but in production. So I'll give one more example of the complexity. But let me just explain how Ford has managed the problem of complexity successfully. They've done two critical things, which they didn't have to do in 1964. The two critical things are one structural and one dynamic.